where were we? I think we just finished writing this tokenize function. So now we need to see if we can rebuild, and it turns out that we cannot rebuild to test this because we have an error. And the error that we have is that the makefile is wrong. So let me go ahead and fix that. Key problem here in the makefile is that it's always going to deal with the first source file, so I'm gonna have to do that because of course I am. That's obviously the fix. Now I type make. Now I type make, and we get a different error. So now we have to make sure that read number in tokens.c actually has types in its signature. So we want a char pointer, text, and a long II. Now we can type make again. Now we have a new problem. So we need to include standard lib. Of course, there's a whole bunch of errors. Next up, tokenize takes a const char pointer text and returns a list, whereas in the header, it takes a just char pointer. We want to take a const char pointer because we're not mutating the input string. But if we're not mutating the input string, that means that over here in tokens, this has to be const char pointer, which is fine. Oh, so now we do the thing, we don't print anything. So back in main, we need to include list.h because we're going to print list tokes. So if we give 1 plus 2 plus 3 times 4, you can see we have spaces around these guys, but not over here. We get 1 plus 2 plus 3 times 4, so our tokenization routine is working fine. Next up, we want to parse. So in order to parse, we're going to need to do some more work. Specifically, we can call parse on the tokens, but the result of parsing is going to be an abstract syntax tree, which is going to be a new type called a calc AST. And then we're going to go ahead and print out that AST just to see what we got. To do that, we're going to need a couple of moving parts. We need our AST, because that's our new type, and then we're going to need our parse function, which is going to be defined in another thing. So let's start off by building our AST. So our abstract syntax tree if ndef is a new structure. So this is a recursive data type because we need to be able to represent a tree. There are two cases of a recursive data type. The first case is that we are a leaf node in the tree, and in that case we're just going to store a number as a value because all the leaves are numbers. The other case is that we have two sort of children of this node. We have an internal node with two children. And in that case, there's two arguments, arg0 and arg1. Now, we need to be able to differentiate between the case where we have two children and the case where we're a leaf, but we also need to be able to know what operator we are if we're an internal node. So we're going to specify our operator as one character, and then the rule is that op is either one of plus minus star or slash for an operation. So for an internal node, op is going to be one of those characters. Or we're going to have that op field contain the character equals if this is a leaf node and this just contains a value. This is a slight waste of space compared to having some sort of enumeration, like tagged enumeration, where we really do have different structures for internal nodes and leaves, but it's not worth saving space in this case. This is a simple solution. So that means we want two sort of constructor functions. So if we have a value, we just pass it the value and it's going to make a leaf node. If we want to make an internal node, we're going to pass it the operator and its two children, and it makes thingamadoos. These guys return pointers. We need a way to clean up that pointer. We need to be able to evaluate an AST to get a value. And we need to be able to print an AST for debugging, and because that's what our program does right now. So with that, let's go ahead and implement these 5 functions over in AST.c. So we're clearly going to need standard lib.h for malloc, standard io.h for print AST, and that's, I think, all I need right now. So to make an AST value, we're going to say calc AST is malloc size of calc AST. We're going to say AST op is equals. We're going to say AST value is VV, and we're going to return AST. To make an operator, we'll say AST arrow op is op. AST arrow arg0 is a0, arg1 is a1, and then we'll return that AST node. To free an AST, we have a little bit more complication here, because we would like to be able to have simple code that can handle either of these two cases. So to make that easier, I'm going to go ahead and say AST arg0 is 0 and AST arg1 is also 0, because that lets us do the same pattern that we've done for our recursive data types before, which is to check whether there's anything in there, check for a null pointer. And then we can just go ahead and do a nice clean recursion. We're not going to handle eval right now, because we're not there yet. Instead, we're going to go ahead and handle printing, because we want to be able to print it out for debugging. So this is sort of putting off the problem. To print an AST, first we transform it into a string, and then we print the string. But sometimes that's the easiest way to solve the problem, and in this case I want to solve it this way because it lets us handle our recursive data structure recursively without worrying about printing, which is not part of the recursion. So if AST op is equals, then we have a value. We're going to allocate some space. Alright, question. Why did I pick 16 as the size that we're going to allocate for this sprintf buffer? Okay. So the value that we have here, AST value, is an int. On AMD64, that means it's a 32-bit int. The maximum value of a 32-bit int is 4b. So that's 4, not quite billion, but not thousand, not million, but billion. So that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is the maximum length of a decimal thing. So 16 is plenty of space, and it's the next sort of power of 2 up. And that'll always be plenty of space to fit that particular result. Sprintf does the thing that we'd expect, and is just like printf, except instead of printing the result, it's going to fill in a buffer with the result. In the other case, we're going to say that the left side is what we get if we go ahead and AST string the left side. The right side is the thing that we get if we AST string the right side. We're going to go ahead and make a real big buffer, which should be big enough to go ahead and work on our string. And then we're going to sprintf into a single string our left side, our operator, and our right side. Then we can free the things that we got from the 2 recursive calls, and then return the new thing. So we're creating a relatively large buffer, but we're only going to be returning one of these size 128 buffers. That won't always work. This may go wrong, but this should be good enough to debug with. Now we can go ahead and type make. We discovered that we don't have a parse function at all. That makes sense. We have to write it. Alright, so this is going to be if endf parse h, define parse h endf. Parse is a function which is going to take a list of tokens and produce an AST. We're almost to the end of this, but there's still some more work to do. So there's a couple moving parts here. We're going to use a sort of tricky strategy that doesn't actually work. That's an important thing to keep in mind about this parse function, is that it is technically wrong, but it will work for my demo. Try to keep an eye out for why it's wrong, and try to think about how you can make it right. So if length of tokes is 1, then we can go ahead and make the assumption that our expression is just a number, because the possibilities are we have just a number, that's the base case, so it's going to be length 1, or we have an expression with an operator, and if there's an operator it has to be at least length 3, because we have to have something on the left, an operator, and something on the right. So we're going to go ahead and translate that token into an integer, and then we're going to return make AST value of that integer. So that's the base case. So the operators that we're worried about are plus, minus, times, and divide. We're going to loop through those operators. And for each operator, we're going to ask, does our list of tokens contain that operator? If it does, then we're going to find the first index in the array where that token appears, where that operator appears. We're going to split off the left half of the array, the things to the left of that operator. We're going to split off the right half of the array on the other side of the operator. Then we're going to construct a AST with that operator and the recursive parsing of the left half and the recursive parsing of the right half. This is not how one traditionally does parsing for a variety of reasons, but it does work well enough for this demo, even if it doesn't end up being quite perfect. So we're going to need some helper functions to make this work. Oh, right, and we need to handle the case where we aren't done. We're just going to exit if we get a bad token stream. So, first helper function that we need is find first index. Actually, I'm going to make an even better helper function. Int streak. So this is going to return if two strings are equal, which is just sort of trivial. All right, next thing that we're going to do is we're going to create that find first index function. So we're going to loop through our list. If we find the token, then we'll return the index. Otherwise, we're going to return -1 just as a signal that we didn't find anything, which turns out to be relevant for our next helper function. Which is going to ask if a list contains a token. Which is going to ask whether we didn't get -1. So if it has a first index, then the string is in the list. Finally, we need slice. Now I want you to think a little bit about this. What we have is a list, and we have a first index and a last index. And what we need to do is generate a new list containing the elements from the input list between those two indexes. How do we do that? There's a couple solutions. The one I'm going to go with is 2 loops. So we're going to start with our whys list and an iterator list. And we're going to go ahead and loop through our input list, skipping elements until we get up to I0. And then we're going to loop over our input list some more, looping over, copying items into our output list until we get up to I1. But that produced a backwards list, so we need rev free. And with that, this should work. It didn't work. We need standard lib. And we need studio. And we need tokens on line 51. So this is actually supposed to be tokes, because that's the name I use in a bunch of places. Need a comma on line 59 over in ast.c. Need a comma right here. Alright, so this is successfully tokenizing our expressions. It's successfully parsing the token list into a tree. And we can see that it does sort of the right thing here. If we do 1 plus 2 divided by 3 plus 4. That's going to do the division first, and then it does the additions afterwards. Alright, so next thing is we want to actually go ahead and do the eval. So that's here in ast.c. 5 is the wrong answer. Instead, we want to do a sort of switch on ast arrow op. If we get an equals, that means we can just return the value because we're a leaf. If we get a plus, we can actually go a little bit more compact than this. So let's do if ast op is equals, then we'll return that value. Otherwise, we know we have a operator majig. So we can do int x is going to be ast eval ast arg0, int y is ast eval ast arg1, and now we'll do a switch on ast arrow op case plus return xx plus yy, case minus return xx minus yy, case star return xx times yy, case slash return xx slash yy, default abort, because those were all the options. Now we're going to go ahead and do another make. Oh, right, we need to, back in calc, rather than printing our AST, we want to say int yy is eval, sorry, ast eval, that ast, we go ahead and print out our result. So we build calc 1 plus 2, 2 times 2 plus 3 times 4. That was our example. We got 16 as expected, so I'm going to declare victory. Definitely take a look and find the cases where this logic is incorrect and our parser is actually where the bug is, and our parser produces incorrect trees for arithmetic expressions. But yeah, that's what I wanted to cover for today, and I'll have homework 5 posted at some point where you will be writing a tokenizer for something. Alright, good luck and have fun.